And good evening, AP Physics students. Mr. Gerson coming at you here, talking about lenses today. I hope you're feeling very focused because I think you're going to find this to be an enlightening lecture. So lenses let people with bad eyes like me see. Lenses can let us look at the stars or look at objects far away. How do these things called lenses work? So a lens is made out of glass, and glass has a different index of refraction than the air. So the lenses can bend light. And because of that, the images that we see may look different. So let's talk about two big categories of lenses that we have: converging lenses that look like this, and diverging lenses. So if I have light coming in parallel rays, and the lens focuses that light to a single point, that is called a converging lens. Okay, and for a converging lens, the focal length, which would be the distance from here to here, is thought to be positive. So in our sign convention, converging lenses have a positive focal length. Diverging lenses, however, have a negative focal length. So for instance, here the light diverges, but if you were to trace these rays all backwards along their diagonals, they would meet at some point here. So the distance from the middle of the point to this kind of imaginary point back there is called the focal length of a diverging lens, and that has a negative sign. Speaking of which, if I place an object on one side of a lens, okay, and it appears on the other side of the lens, kind of where it's supposed to, that is called a real image. So again, it's actual light that's forming the image. And for lenses, real images get formed on the other side of the lens. Now, most of the time, converging lenses make real images, but you have to be careful and use your lens equation and draw your ray diagrams, because depending upon where you are, either lens, if the circumstances are right, can form real or virtual images. So I gave it away here. There are also virtual images, and virtual images are formed on the same side. So if this were my object and my image got formed over here on the same side of the lens, then that would be called a virtual image. So with lenses, real images on the opposite side, again, actual light's going through, and virtual image on the same side. And again, you have dotted lines coming back through on your ray diagrams to form virtual images. So there's two ways to figure out with lenses where your image is going to be, and if it's going to be magnified or inverted or real or virtual. You can draw your three ray diagrams, right? The same three ray diagrams or rays as you did with mirrors. Your P ray, your F ray, your C ray, right? The only difference is your C ray goes through the actual center of the lens instead of through the center of curvature. Now, you can still also use, and I actually encourage you whenever you come across a lens equation, to both draw a ray diagram and also use the thin lens equation, okay? This guy right here, which is on your equation sheet, can not only be used for concave and convex mirrors, but it's where it's called the mirror equation, but it's also called the thin lens equation, okay? So here, F would be your focal length, again, positive for converging, negative for diverging. DO would be the object distance, and DI your image distance. Again, DI here would be positive for real images, and DI would be negative for virtual images. All right. Okay. Also, why do we have lenses? Sometimes lenses can bring things into focus. Sometimes lenses can magnify, okay? The height of the image divided by the height of an object, so a lens's magnification, is equal to negative di over do, okay? Now, if m is positive, the image will be upright. That is, it won't be flipped, okay? For instance, this image here, this started out upright and ended up upright. If m has a negative sign, then the image will be inverted, okay? Now, I kind of went over a lot of sign conventions here for real images, virtual images, converging lens, diverging lenses, and sometimes it's kind of hard to keep them all straight. So your book did a nice job on page 651 of really summarizing all the sign conventions. And there are kind of a lot of them. Don't try to memorize them all, but just try to, as you're doing the problems, keep referring back to this. And after a while, the sign conventions start to really kind of sink in and you just kind of get a feel for them. And always use, when you're solving a problem, both the ray diagram and the thin lens equation. And usually if you blow a sign in one, you can use the ray diagram to figure out what your sign mistake was here, or vice versa. Well, let's go ahead and move on, and let's start you out here on problem number, and you know what? I screwed this up, you guys. I didn't want to do problem number 48. I wanted to do problem number 43. All right, Mr. Kirsten needs to write a little neater here, okay? So I'm going to start out problem 43, and I'm going to do, so this is problem number 43. I'm going to do part B first. Part B says I have an object, I have a lens, and the focal length of the lens, it's a converging lens with a focal length of 65 millimeters. Furthermore, it states that the image formed by the lens is on the other side of the lens, and that the image is formed, a clear image is formed, 78 millimeters from the lens. And then it asks us to solve for the object distance, okay? So I'm going to use my thin lens equation here. And if I do a little algebra here and type in this all into my calculator, I get that the object distance is a positive 390 millimeters. Now, I wouldn't have to do this, but just for kicks, I am going to plug this in to the magnification equation. Oops, sorry, that's positive. And find that this lens combination will make a magnification of negative 0.20. Okay, now part A says draw the ray diagram. And I was going to draw this for you, and it's kind of a big diagram, and I tried drawing it a couple times, and I can't draw lines very straight here, so I'm going to cheat here, all right? So we're told that the focal length F here is 65 millimeters, so that's what that would look like. The image is at 78 millimeters away. And then, as it said, our object was 390 millimeters away. Notice a couple things here. The magnification, which we didn't have to solve for, but we did anyway. The magnification turned out to be a negative 0.2. And notice here in the ray diagram, the image is inverted. It's the opposite, right? It's going down versus up. And it's only about 0.2 times as large, okay? Notice the object distance, image distance is positive, meaning this is a real image. This is our lens, with our three rays here. Our parallel ray, which ends up going through the focus. Our F ray, which goes through the focus and then ends up going parallel. And then our central ray, which goes straight through the center of the lens. So between those three rays in your ray diagram, and of course your good old thin lens equation, you should be able to figure out any lens problem. All right. So nice work, AP Physics students. I got a neat little article to share with you here. So I know it's April, and we have been experiencing quite a bit of snow, and I know that all of that snow can be quite upsetting. But let me share with you an article about snow here. So here's our article. So you guys think we've gotten a lot of snow here? This is a article from Popular Mechanics about the most latest Antarctic ice station or scientific station. What's happened is they've lost the last 4 installations they've made down there. Due to falling off the ice sheath, getting buried in snow, blizzards, and that type of thing. So this thing is actually on skis with legs, and the legs and skis can actually move so that independently of each other, so it can stay up on top of the snow. So just in case you were thinking, oh my gosh, we've been getting so much snow, at least your house doesn't have to have movable stilts on it to keep it above the snow. All right, nice work, AP Physics students. We'll see you tomorrow.